This video explains the analysis procedure according to AS3600, that is strain, stress and force calculations and equivalent rectangular stress block theory. Now, first of all, for AS3600 concrete design, the Australian standard AS3600 give us the strain value for both steel and concrete, and based on the given strain value we can calculate the stress for the steel and concrete. Now the reason that Australian standard don't give the stress, because the stress are varied. Like for example, in the concrete, for the same strain we have different stress value. For examples, I can give you an example here, that if I have a strain value, if the Australian standard give us the strain value, we should get the concrete stress here, and definitely for that case we will get the different strain value. So for example, if I take the strain value here, I should have a steel stress value here, and concrete stress value here, and steel stress value here. So we have different stress values. So based on the given strain value we can calculate the stress. Now for steel, this is the elastic region, so we can multiply the strain with the Young modulus of the steel. Generally they are 200,000 Newton per millimeter square. That's the Young modulus of the steel. So given strain times the Young modulus give us the stress in the steels, and for calculating the stress in the concrete we will take the rectangular stress block theory. Now to calculate, once you calculate the stress, this strain is given in the Australian standard. We first calculate the stress, and from the stress we multiply by the area of the cross section of the steel and concrete, and then we get the force. Now the next one is the equivalent rectangular stress block theory that I'm going to discuss for the design of beam. Now in that case we can take this rectangular stress block theory here. Now start with very small rectangular cross section of the concrete. We have a width B, depth D. In that case we have a reinforcement on the tensile side. I'm taking this one is a sagging bending moment. So if I take the rectangular beam, it would bend in that fashion. So in that case we have a tension region at the bottom, and we have a compression region at the top, and this neutral axis is dividing the region of compression and tension. So that is a neutral axis, that is NA is a neutral axis. So top portion is compression and then tensions. Now let's get the strain value, because these are the composite structures. Steel and concrete work as a one member, like they bond together to work as the same. So both steel and concrete subjected to the same strain. In that case we will get the linear strain distribution. Now in Australian standards, for the concrete, the top fiber of the concrete, the maximum compression strain given is 0.003. So if I show it in the diagram, I'm talking about this maximum value that we get is 0.003. that is for concrete strain, that is given in the Australian standard. Where it's gonna given, I'm going to show you. Now in Australian standard, if you go page number 110 in AS3600 2018, we have a rectangular stress block theory in clause 8.1.3. in that one it has clearly written here that maximum strain in the extreme compression fiber is taken as 0.003. that's the value is coming from. In extreme compression fiber means that the fiber, the line that is far from the neutral axis, that the top edge. So the strain at this edge of the concrete in the compression region is 0.03, given in the Australian standard on page number 110 in the clause 8.1.3. now once you know the strain, as I mentioned, we have a procedures to say strain, we can go calculate the stress. Now to calculate the stress in the steel is quite easy. Once you know the strain of these steels, we can multiply with the Young modulus to get the stress. Now this one is a little bit complex because this is the non-linear behavior, unlike the steel. So you can see this is non-linear behavior of the concrete. As you can see, that is non-linear behavior, so it's not straightforward to calculate the stress from the strain. We know the strain is 0.03, but we can't calculate it straight away. Now in that case, we can use this theory that, let's say this is the equivalent. I draw it here, B and D. Now as you know, this is the zero value for the strain. So when you have a 0 value of strain, you have stress is 0 in concrete. I'm just following the blue line. As this strain increasing, as this strain is increasing, our stress are increasing as well. As you can see, the stress are increasing as well. It reach at the top and it goes down. So it goes down here. So that's what the equivalent. So if you have this linear strain diagram, so zero stress 0, I'm just following here, 0 0. I'm just taking it from here. We have 0 here, 0 as a stress increasing, strain increasing. We have a stress increasing, we have reached the maximum point, and then it's reached here. So this value, this is maximum, is 0.9 FC, right? So that is the maximum stress. So this is the compression state, and we just reduce it by 10% because the concrete we make it at the site. So to allow that safety factors, we allow the material variation at the construction site, we multiply by 0.9. Now it's very difficult to calculate the area for this kind of parabolic shapes. We need to calculate the area. Generally rectangular area is very easy to find. So what happened, the Australian standard has converted this parabolic area into equivalent this area. In that case, what we need this one, and we need this value. There we need two values to convert into equivalent. Now the Australian standard has given the lambda value. Australian standard has given lambda value. I will show it in the examples. That lambda you multiply by dn, and also given alpha 2 value. So we can find this width and this width to calculate the area. So that's how we get this rectangular shape with alpha 2 FC dash and lambda dn. Once you know the stress, we can convert force by multiplying the area. So that is the compression stress in the concrete, and that is the tensile stress, tensile force in the steel, and this is the compression force in the concrete. Now it's a quite simple phenomena to calculate stress to force. I'm going to show you one simple examples, that if I like to calculate this force in the concrete. Let's say this is a force in the concrete. We have a stress times area. Now we know already stress is alpha 2 FC dash, that is alpha 2 FC dash times the area. Now very easy to see here, the area of this block is this area, right? Not this whole area, because as you know, this is a parabolic shape, so we can't just multiply B times dn. This is incorrect. We need to get this equivalent area. Now that equivalent area has a depth of lambda dn. So if I have this lambda dn here, and we have a width b, so the area of this rectangular block is b times lambda n, and the stress is alpha 2 times FC dash. That's how we calculate the force in the concrete section. Thank you very much.